You hear whispers in deep space forums, amateur astronomers staring at their monitors in Chile, Hawaii, California, July 1st, 2025. A signal trips the asteroid Terrestrial Impact Last Alert System telescope in Rio Hurtado. Not bound to the sun, moving 58 kilometers per second at infinity, eccentricity 6.137. The third, confirmed visitor from beyond our solar neighborhood, tears through the dark on a trajectory nobody predicted. They name it 3I Atlas, Manhattan-sized nucleus, faster than anything we have caught before from outside. And on October 29th, 2025, at exactly 11:27 Universal Time. When it swings closest to the Sun at 203 million kilometers, 1.36 astronomical units, tucked between Earth's orbit and Mars, something happens that splits the astronomy community clean down the middle. Davide Farnocchia sits at NASA's Jet Propulsion Laboratory in Pasadena, PhD from the University of Pisa, navigation engineer who tracks asteroid orbits, measures non-gravitational perturbations, calculates whether near-Earth objects pose impact threats. He files a report into the Small Body Database, two components of acceleration measured in the orbital plane. Radial push away from the Sun, 135 kilometers per day squared. Transverse acceleration relative to the Sun's direction, 60 kilometers per day squared. Not gravity, not radiation pressure from sunlight. Not the Yarkovsky effect where absorbed sunlight creates a thermal push on spinning rocks. This is something else. The object deviated from pure gravitational motion by roughly 10 times Earth's radius over 1 month. At the Atacama Large Millimeter Array in Chile's high desert, radio dishes lock onto 3I Atlas near perihelion. The comet sits 4 arcseconds away in right ascension, from where gravitational models say it should be, 4 arcseconds. Roughly 0.001 degrees. Measurable. Undeniable. Published in Orbital Updates, filed October 29th through early November. If you value documented interstellar science and rigorous orbital mechanics like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's Jet Propulsion Laboratory Small Body Database Orbital Solutions, computed by navigation engineer Davide Farnocchia, published October 29th through November 5th, 2025. The Atacama Large Millimeter Array observational data, confirming the 4 arcsecond right ascension deviation from predicted trajectory, published in late October, and Avi Loeb's analysis papers posted on Medium between October 30th and November 5th. Drawing from his position as director of Harvard's Institute for Theory and Computation, and 11 peer-reviewed papers on 3I Atlas published between July and November 2025. These aren't press releases, these are orbit fits. Telescope measurements, momentum calculations. Now back to the information. Comets outgas, ice sublimates under solar heat, water, carbon dioxide, carbon monoxide, methane, ammonia, volatiles locked in the nucleus since formation 4.6 billion years ago or longer, turn directly from solid to gas, no liquid phase. The escaping gas acts like a rocket thruster. Newton's third law, action and reaction. Mass ejected one direction pushes the nucleus the opposite way. This creates what astronomers call non-gravitational acceleration. It's why comet trajectories deviate slightly from pure Keplerian orbits, dictated only by the sun's gravity. Every active comet does this. Halley's Comet, Hale-Bopp, Shoemaker-Levy 9 before Jupiter tore it apart. All showed measurable non-gravitational forces from outgassing. The phenomenon is well understood, predicted, expected. But 3I Atlas is not like other comets. Discovery date, July 1st, 2025, by the Atlas Survey Telescope. Pre-discovery images found in archives going back to May 15th. Zwicky Transient Facility caught it May 15th. Atlas logged first detection April 27th at 3 sigma confidence. Orbital analysis confirmed hyperbolic trajectory within days. Not elliptical, not bound to our star. Eccentricity over 6 means it traces nearly a straight line through the system. Velocity at infinity, 58 kilometers per second. Compare that to 1I Oumuamua at 26 kilometers per second, 2 and I Borisov at 32. 3I Atlas moves nearly twice as fast as the first interstellar visitor. Its orbit tilts only 5 degrees from the ecliptic plane, the flat disk where planets orbit. Random interstellar objects entering the solar system should arrive from any direction with equal probability. The chance of alignment within 5 degrees of the ecliptic, 0.2%. Between July and September, Chasus, the James Webb Space Telescope measured a mass loss rate of 150 kilograms per second from 3I Atlas. Constant, steady. Gas streaming off the nucleus as solar radiation heated the surface. But here's the critical point. That mass loss produced no detectable non-gravitational acceleration. Analysis of 4,022 astrometric data points from 227 observatories worldwide, covering July through September, showed the comet moving exactly where gravity alone would place it. The trajectory matched gravitational predictions to within observational uncertainty. No rocket effect, no deviation. Then perihelion happens. October 29th, distance from Sun, 203 million kilometers. Closest approach, peak solar heating. And suddenly the orbit shifts. Radial component, 135 kilometers per day squared outward from the Sun. Transverse component, 60 kilometers per day squared. Total magnitude of non-gravitational acceleration, roughly 0.02 millimeters per second squared. Small by human scales. Massive by celestial mechanics standards for an object this size. Momentum conservation gives you the physics. Force equals mass times acceleration. For a rocket, force also equals exhaust velocity times mass loss rate. Set them equal. Acceleration equals ejection speed times mass loss rate divided by total mass. Flip it. The time scale to lose half the mass equals ejection speed divided by measured acceleration. Thermal sublimation of water ice produces gas moving a few hundred meters per second. Plug in 300 meters per second, divide by 0.02 millimeters per second, squared. Convert units. You get 6 months, 6-month half-life. Over the 1 month it takes 3I Atlas to cross a distance comparable to its perihelion separation from the Sun. It should lose 1/6 to 1/10 of its total mass if the acceleration comes from standard cometary outgassing. Calculate the mass. Earlier measurements by Webb in August and September gave nucleus diameter estimates between 440 meters and 5.6 kilometers. Assume intermediate size around 2 kilometers. Cometary densities run 400 to 600 kilograms per cubic meter, low because they're porous, ice and rock. Take 500. Volume of a sphere 2 kilometers across, roughly 4 cubic kilometers. 4 billion cubic meters times 500 kilograms per cubic meter equals 2 trillion kilograms, 2 billion tons. Conservative estimate, lose 1/6 of that near perihelion, 330 million tons, ejected over 1 month. That's a mass loss rate around 125,000 kilograms per second, compared to the 150 kilograms per second measured before perihelion, increased by a factor of over 800 enough. Such massive evaporation should create a visible debris cloud. Not a faint coma you need a large telescope to detect. A massive plume of gas and dust carrying hundreds of millions of tons of material expanding outward at hundreds of meters per second. Spectroscopy should light up with emission lines from water, carbon dioxide, carbon monoxide, hydroxyl radicals, cyanide, dust continuum. The cloud would span thousands to tens of thousands of kilometers, easily detectable from Earth-based observatories. Once 3I Atlas emerges from behind the Sun in early December. Webb Space Telescope, Hubble, ground-based instruments, all capable of measuring such a plume if it exists. But here's where the story twists. Observations from the Stereo spacecraft, SOHO Solar Observatory, and GOES-19, weather satellite during September and October 2025, captured 3I Atlas as it approached perihelion, published in a preprint paper posted to Archive on October 30th. Document number 251.0.25035. The comet brightened rapidly, magnitude scaling inversely with distance from the Sun to the power of -7.5 plus or minus 1. Normal comets brighten with an inverse distance power between 2 and 4. 7.5 is extreme, unprecedented in the comet database. The brightness surge implies either massive outgassing or something else entirely. And the color? Comets redden as sunlight scatters through dust in the coma. Dust grains absorb blue wavelengths more efficiently than red, so reflected light shifts toward longer wavelengths. The surface temperature of 3I Atlas at perihelion should be roughly 300 Kelvin, cool compared to the Sun's photosphere at 5800 Kelvin. Cool objects emit and reflect redder light, yet stereo, SOHO, and GOES-19 data show 3I Atlas appearing bluer than the Sun near perihelion, not redder. Bluer. Published October 30th, same RNF paper. The spectrum shifted toward shorter wavelengths. Potential explanations. Ionized carbon monoxide emissions at specific blue wavelengths could tilt the color balance. Ko+ ions emit strongly in the blue and ultraviolet. but the required CO plus concentration would be massive, far beyond what any known comet produces. Alternative explanation: a hot source at several thousand Kelvin emitting thermal radiation that peaks in the blue. Natural cometary processes don't create such temperatures. Solar heating alone can't do it. The nucleus isn't a star. Avi Loeb at Harvard publishes his analysis October 30th on Medium, director of the Institute for Theory and Computation. Authored 11 scientific papers on 3I Atlas between July and November 2025. His calculation: if the non-gravitational acceleration comes from outgassing, 3, I Atlas must have lost at least a sixth of its mass, potentially more, to explain the measured force components. That mass should form a detectable cloud carrying over 5 billion tons of material. If observations in November and December reveal no such cloud, then cometary evaporation is not the explanation. Published October 30th, 6 days after perihelion. The clock starts ticking. Dark comets enter the discussion. Objects on asteroid-like orbits that show non-gravitational acceleration but no visible cometary tail or coma. Discovered starting in 2023. By December 2024, astronomers identified 14 dark comets in the solar system. Two populations: outer dark comets measuring roughly 1 kilometer across on elliptical orbits farther from the Sun, inner dark comets around 10 to 100 meters across on circular near-Earth orbits. All exhibit non-gravitational acceleration inconsistent with radiation pressure or Yarkovsky thermal effects. All look like asteroids in images: no dusty tails, no gas clouds visible even in deep exposures, yet they accelerate like comets. First interstellar object, 1I Oumuamua, discovered October 19, 2017 by the Pan-STARRS telescope in Hawaii. Reddish color, elongated shape, length to width ratio at least 5 to 1, possibly 10 to 1. Tumbling through space every 7 to 8 hours, hyperbolic orbit, eccentricity 1.2, past perihelion. September 9, 2017, at 0.25 astronomical units inside Mercury's orbit. Exhibited measurable non-gravitational acceleration starting in June 2017 as it departed the inner solar system. Magnitude: 0.0005 millimeters per second squared. Small, but statistically significant. Spitzer Space Telescope observed Oumuamua in November 2017. Detected no infrared excess, no dust, no gas emissions. Published December 2018 in the Astronomical Journal. Non-gravitational acceleration without visible outgassing. Comet experts called it a dark comet. The term became shorthand for objects exhibiting cometary acceleration without a cometary appearance. 3, I Atlas, shows a coma. Visible in Hubble images from July 21st, 2025, when the comet sat 277 million miles from Earth. Teardrop-shaped cocoon of dust extending roughly 2 to 3 arc seconds from the nucleus. Faint antitail pointing toward the Sun, unusual geometry, but consistent with small dust particles pushed by radiation pressure at high ejection speeds. By August 27th, Gemini South Telescope captured the development of a conventional tail pointing away from the Sun, stretching 30 arc seconds, or roughly 56,000 kilometers. Coma diameter on September 15th, 180,000 kilometers, asymmetric, elongated in the antisolar direction. James Clerk, Maxwell Telescope measured hydrogen cyanide production on September 7th at 1.5 times 10 to the 25th molecules per second. By September 14th, cyanide production climbed to 4.5 times 10 to the 25th molecules per second, 3 times higher in 1 week. Dust tail visible, gas emissions confirmed, standard cometary activity. But the mass loss rate before perihelion, 150 kilograms per second in August and September, did not produce any non-gravitational acceleration detectable in the trajectory. 4,022 astrometric measurements from 227 observatories showed purely gravitational motion, then perihelion. Suddenly, acceleration. The disconnect raises questions. Post-perihelion data arrives. Minor Planet Center and JPL Small Body Database release. Updated orbit fits November 5th, 2025. New observations spanning October 31st through November 4th. The comet brightened by a factor of roughly 5 in the green band, centered at 0.464 micrometers, compared to observations from October 5th through 8th. Non-gravitational acceleration value revised downward by about 1/3 compared to the October 29th fit. Still statistically significant at 3.7 standard deviations above zero. The detection is robust. The acceleration is real. Measured at the updated perihelion distance of 1.38 astronomical units, 206 million kilometers from the Sun. Europe's Jupiter Icy Moons Explorer spacecraft, JUICE, scheduled observations of 3I Atlas in early November. JUICE launched April 14, 2023 from French Guiana. Currently en route to Jupiter for arrival in July 2031. Carries cameras, spectrometers, ice-penetrating radar, magnetometer, particle detectors. On November 2nd and November 25th, JUICE instruments can observe 3I Atlas from a distance of roughly 0.3 astronomical units, less than 1/3 the Earth-Sun distance, 10 times closer than Earth's view at that time. If 3I Atlas lost hundreds of millions of tons of material near perihelion, JUICE's ultraviolet and visible light spectrometers should detect emission lines from water, hydroxyl, carbon monoxide, carbon dioxide, cyanide, MO. The plume would be obvious. As of November 5th, no public release of JUICE data confirming or denying the presence of a massive gas cloud. December 19th, 2025, 3I Atlas reaches closest approach to Earth, 1.8 astronomical units, 269 million kilometers, 167 million miles, far enough to pose zero threat, close enough for detailed spectroscopy. Hubble Space Telescope, scheduled for ultraviolet observations to measure sulfur to oxygen ratio and gas composition. Webb Space Telescope, scheduled for infrared spectroscopy in December to probe the interior chemistry of the nucleus, not just surface skin, but what volatiles remain deep inside. Hundreds of ground-based observatories will track the comet. If a massive debris cloud surrounds 3I Atlas, December observations will confirm it. If no such cloud exists, then the non-gravitational acceleration measured near perihelion cannot be explained by standard cometary outgassing. Alternative hypothesis, technological propulsion. Loeb raises it October 30th in his Medium post, published again October 31st, November 1st, November 5th. Not as speculation, but as logical deduction from the data. If no massive gas cloud appears in December, if the comet did not lose a sixth of its mass, if spectroscopy does not show the expected emission signatures, then the acceleration must come from something other than sublimating ice. A rocket engine expels exhaust at much higher velocities than thermal gas from sublimation. Chemical rockets, 2 to 4 kilometers per second. Ion drives, 20 to 50 kilometers per second. Nuclear thermal propulsion, 8 to 9 kilometers per second. Higher exhaust velocity means less mass required to produce the same thrust. An engine could create the measured acceleration while losing only a small fraction of the total mass, potentially undetectable in observations. The blue color, near perihelion, fits an engine hypothesis. Hot exhaust glowing at thousands of Kelvin emits thermal radiation that peaks in the blue and ultraviolet. Artificial light sources, lamps, LEDs, plasma, also produce blue-shifted spectra. Natural cometary processes do not generate such temperatures or colors. Dust reddens light. Gas emissions from sublimation produce discrete spectral lines in the ultraviolet, visible, and infrared at ASIG. Not a broad thermal continuum shifted toward blue wavelengths. 9 anomalies compile in Loeb's November 1st analysis. First, retrograde trajectory aligned within 5 degrees of the ecliptic plane, probability 0.2%. Second, sunward jet in July and August, antitail that is not a geometric illusion from viewing angle, confirmed by Hubble and Gemini observations. Third, nucleus mass roughly 1 million times greater than Oumuamua, 1,000 times greater than Borisov, while moving faster than both. Combined probability less than 0.1%. Fourth, arrival time, fine-tuned to bring 3I Atlas within tens of millions of kilometers of Mars on October 3rd, Venus on November 3rd, Jupiter on March 16th. 2026, yet unobservable from Earth at perihelion due to solar conjunction. Probability 0.005%. Fifth, gas plume contains much more nickel than iron, and a nickel to cyanide ratio orders of magnitude larger than any known comet, including 2I Borisov. Nickel to iron ratio matches. Industrial nickel alloys, probability below 1%. Sixth, Webb telescope measurements in August 2025 show water to cyanide ratio significantly lower than expected for natural comets. Seventh, the antitail in July persisted for weeks, unlike typical antitails that are transient geometric projections. Eighth, rapid brightening scaling with inverse distance to the negative 7.5 power. Ninth, blue color near perihelion instead of expected reddening. Each anomaly considered alone has low but non-zero probability. Combined, multiplying probabilities for independent anomalies, the likelihood drops to vanishingly small numbers. Either 3I Atlas represents an extraordinarily rare natural configuration, or something else is occurring. Scientific method demands attention to data over theory. Loeb references cosmology. At Harvard's Institute for Theory and Computation, he leads weekly luncheons attended by over 100 astrophysicists. Presentations cover latest advances. October 30th session discussed the Hubble tension, discrepancy between the expansion rate of the universe measured from cosmic microwave background versus local distance ladders using Cepheid variables and supernovae, 7 sigma tension. Real. No theoretical explanation fits elegantly. Loeb's comment to the young theorists in the audience: "It is bad professional practice for theoretical astrophysicists to conclude that the data must be wrong just because they do not have a theoretical explanation for it. Same principle applies to 3I Atlas. Data shows non-gravitational acceleration. Data shows blue color. Data shows extreme brightening. Data shows trajectory aligned with the ecliptic. Data shows sunward jet. Data shows high nickel. Observations precede interpretation. Measurements precede models." But most astronomers disagree with the technological hypothesis. Megan Schwamb at Queen's University Belfast tells Newsweek November 2nd, "If there is an increase in the rate of volatile ices that are sublimating off the surface of the comet, then 3I Atlas would be observed to be speeding up. We see this effect in long period and short period comets. This happened with Oumuamua. Spitzer observations detected a deviation in its orbit caused by non-gravitational accelerations due to suspected outgassing of some volatile ice." She continues, "There is a significant amount of peer-reviewed literature of the data collected after 3I Atlas was discovered, and as it has continued to move closer to the Sun. The analysis of these efforts from many astronomers around the globe show that, to the best of our knowledge, 3I Atlas is consistent with having a natural origin. Its properties to date are consistent with it being an icy planetesimal that formed around another star in the galaxy and was later gravitationally ejected into interstellar space." Daryl Seligman at Cornell University, who co-authored the original Dark Comet papers in 2023, tells the press that comets are actively losing material and by blowing gas off their surfaces. There are basically rocket-like recoils that make non-gravitational accelerations. This means accelerations can be used to infer outgassing or mass loss. The first interstellar object, Oumuamua, had non-gravitational acceleration and no dust coma. There are also near-Earth objects called dark comets that don't have apparent tails, but have comet-like non-gravitational accelerations. Standard explanations exist. Tom Statler, NASA's lead scientist for solar system small bodies, tells The Guardian, "It looks like a comet. It does comet things. It very, very strongly resembles, in just about every way, the comets that we know. It has some interesting properties that are a little bit different from our solar system comets, but it behaves like a comet. And so the evidence is overwhelmingly pointing to this object being a natural body." It's a comet. NASA acting administrator Sean Duffy responds to Kim Kardashian on social media November 3rd. Kardashian asked, "Wait, what's the T on 3I Atlas?" Duffy replies, "Great question. NASA's observations show that this is the third interstellar comet to pass through our solar system. No aliens, no threat to life here on Earth. Public reassurance, official position." A SETI Institute paper published October 2025 addresses the alien spacecraft claims directly. Lead author compares 3I Atlas's spectral slope with D-type asteroids and interstellar comet 2I Borisov. Finds consistency with natural objects. States that 2I Borisov also underwent non-gravitational acceleration due to outgassing. Argues that if 3I Atlas accelerates, it fits known cometary behavior. If it doesn't accelerate beyond what's observed, it still fits. The paper concludes, "It looks like a comet. It does comet things." Chemical analysis from James Webb and other instruments shows water. Carbon dioxide, carbon monoxide, cyanide, hydroxyl, standard cometary volatiles. The SETI analysis suggests 3I Atlas could be a lithified clastic fragment from an exoplanetary sedimentary basin, a piece of rock from another star system that got ejected and wandered here. Brian Cox, science popularizer and former particle physicist, states forcefully that 3I Atlas is definitely a natural comet. Cox has not published peer-reviewed papers on 3I Atlas. Loeb responds, "Brian Cox did not write a single scientific paper about 3I Atlas. He acts as a science popularizer rather than a researcher who is engaged with the related science concerning 3I Atlas." Loeb authored 11 scientific papers on the object between July and November. He challenges Cox to explain the 9 documented anomalies. International Asteroid Warning Network schedules a campaign from November 27th, 2025 through January 27th, 2026. IAWN coordinates observations across global telescopes to track 3I Atlas during its outbound journey. Goal: refine orbit predictions, measure any further non-gravitational accelerations, detect mass loss, observe changes in brightness and color, gather astrometric and photometric data for planetary defense training. The network notes that comets are especially hard to observe because their tails and comas make it difficult to estimate overall brightness and to pinpoint the nucleus position for precise astrometry. 3I Atlas serves as a test case for future interstellar visitors. Next time an object arrives on a hyperbolic trajectory, IAWN wants protocols in place. Europe's Comet Interceptor mission, scheduled for launch in 2029, ASAS, will wait at the second Earth-Sun Lagrange point, 1.5 million kilometers from Earth on the opposite side from the Sun, ready to intercept an incoming interstellar object or long-period comet. Mission cost: 150 million euros. Operators must avoid targeting artificial space debris by mistake. In 2025, the Minor Planet Center deleted asteroid designation for object 2018CN41 after 17 hours, when observers realized it was Elon Musk's Tesla Roadster launched on Falcon Heavy in 2018. The car orbits the Sun on an eccentric trajectory with a period of 1.53 years, initially cataloged as an asteroid. Removed from the database once spectroscopy revealed stainless steel signatures, space is filling with human artifacts. Distinguishing natural from artificial becomes harder. Dark comets in the near-Earth environment might make up 60% of small objects on certain orbital types, according to a July 2024 study published in the Astrophysical Journal. Authors examined 7 known dark comets and modeled their origins. Hypothesis: these objects came from the inner main asteroid belt via the NU6 secular resonance. They underwent rotational spin-up from Yarkovsky, Torques, and thermal radiation pressure. Once rotation period dropped below a critical threshold, centrifugal forces exceeded tensile strength. The object fragments. Pieces fly off, reducing angular momentum. Each fragment continues to spin and outgas, losing more material, fragmenting again in a cascade. Eventually, the torque is insufficient to spin the fragments beyond their critical rate. They stabilize, small, rapidly rotating, mostly devolatilized, but not entirely devolatilized. Residual volatiles remain, creating weak outgassing that produces measurable non-gravitational acceleration without visible tails or comas. Vera C. Rubin. Observatory's Legacy Survey of Space and Time begins operations July 2025. 8.4 meter primary mirror, 3.2 gigapixel camera, scans the entire southern sky every few nights, designed to discover tens of thousands of near-Earth asteroids, thousands of trans-Neptunian objects, supernovae, variable stars, transient phenomena, expected to find many more dark comets, objects that look like asteroids but accelerate like comets. The population is larger than previously thought. Japan's Hayabusa. 2 spacecraft is set to rendezvous with asteroid 1998 KY26 in July 2031. That asteroid was identified as an inner dark comet in December 2024. Diameter around 50 meters. Circular near-Earth orbit. Non-gravitational acceleration inconsistent with radiation effects. No visible coma or tail. Hayabusa 2 will approach, observe, potentially collect samples. Direct measurement of a dark comet's composition. Internal structure, surface properties. The mission was planned before astronomers classified the target as a dark comet. Lucky coincidence. First spacecraft encounter with this class of object. 3I Atlas will pass 0.36 astronomical units from Jupiter on March 16th, 2026, 54 million kilometers, 33 million miles, close enough for gravitational perturbation. Jupiter's mass will slightly alter the comet's trajectory. After that, 3I Atlas continues outbound. Velocity at infinity, 58 kilometers per second. It will leave the solar system and return to interstellar space, never to be seen again from Earth. Travel time to the nearest star at that velocity, 73,000 years. Origin unknown. Tracing the trajectory backward through the galaxy, accounting for the sun's motion, the motion of nearby stars, gravitational perturbations. Astronomers estimate 3I Atlas could have been ejected from its home system billions of years ago. A paper in the Astrophysical Journal, published August 2025, argues that based on the steep incoming trajectory and the expected distribution of interstellar objects in the Milky Way, 3I Atlas could be 7 to 10 billion years old. older than the solar system. Formed during an earlier epoch of galactic history when the star formation rate was higher, metallicity lower, planet formation dynamics different. An ancient traveler carrying information about conditions in the galaxy billions of years ago. But the anomalies remain. The retrograde orbit aligned with the ecliptic, the sunward jet persisting for weeks, the nucleus mass 1,000,000 times greater than Oumuamua. The arrival time, bringing close encounters with multiple planets yet hidden from Earth at perihelion. The high nickel to cyanide ratio, the low water content, the blue color, the extreme brightening, the non-gravitational acceleration appearing suddenly at perihelion after months of purely gravitational motion. December, observations will test the hypothesis if Webb, Hubble, and ground-based telescopes detect a massive gas cloud carrying hundreds of millions of tons, if spectroscopy shows the expected emission lines at the predicted intensities, if the brightness and color return to pre-perihelion values consistent with cooling and reduced outgassing, then the case for natural cometary activity strengthens. The anomalies become statistical flukes. Rare but possible. 1 in 1,000 configurations that occasionally occur in a galaxy containing hundreds of billions of comets. If no massive cloud appears, if the comet remains bright and blue without corresponding gas emissions, if spectroscopy does not show the predicted sublimation signatures, then the explanation must change. An object that accelerates without losing significant mass, an object that glows blue near the sun without thermal equilibrium with solar radiation, an object with industrial nickel ratios, an object that aligns with the ecliptic, an object that times its perihelion to avoid Earth's view. Loeb writes November 1st, if we do not observe a massive cloud of gas around it in December, then cometary evaporation is not the explanation of its non-gravitational acceleration. Instead, it might constitute a technological signature of a propulsion system. That same logic applied to Oumuamua in 2017. No detected outgassing, non-gravitational acceleration, elongated shape tumbling through space, reddish surface suggesting organic compounds or space weathering. Multiple explanations proposed: hydrogen iceberg, sublimating without detectable emissions, nitrogen iceberg from a Pluto-like exoplanet, fractal dust aggregate held together by weak cohesion, fragment of a tidally disrupted planet, light sail pushed by starlight or laser beam. Each hypothesis has strengths and weaknesses. None is definitively proven. Oumuamua is gone, beyond the reach of our fastest spacecraft, fading into interstellar darkness. We will never get closer. Data. 3I Atlas offers a second chance. Larger, brighter, closer approach to multiple planets, observable by spacecraft at Mars and Jupiter, scheduled for detailed spectroscopy in December, monitored by the International Asteroid Warning Network campaign extending into January 2026. More data will accumulate, better measurements, tighter constraints. The core question, does nature alone explain the observations, or is something else required? Nature has produced 4.5 billion years of planetary formation in this solar system, trillions of comets in the Oort cloud, hundreds of billions in the Kuiper belt. Asteroids spanning sizes from dust grains to Ceres at 950 kilometers diameter. Active asteroids with tails, main belt comets sublimating beyond the frost line, extinct comet nuclei in near-Earth orbits, centaurs crossing between Jupiter and Neptune exhibiting sporadic activity, quasi-Hilda comets near Jupiter's Lagrange points, dark comets accelerating without tails. The diversity is vast. Every new mission, every new telescope survey, every improved spectroscopic technique reveals unexpected complexity. Nature is inventive. Rare configurations happen, but the probabilities stack. Each anomaly reduces likelihood. 0.2% for ecliptic alignment, 0.1% for mass and velocity combination, 0.005% for planetary encounter timing, below 1% for nickel ratio, below 1% for blue color. Multiply them, the product approaches 0. Extraordinary claims require extraordinary evidence, Loeb's statement. But also, extraordinary data require extraordinary attention. Dismissing observations because they do not fit current models is the inverse error. Models serve data, not the other way. When measurements conflict with expectations, either the measurements are wrong, instrumentation error, calibration mistake, misinterpretation, or the expectations need updating. 4,022 astrometric data points from 227 observatories showed no non-gravitational acceleration before perihelion. Then, abruptly, acceleration appears, confirmed by JPL orbit fits, confirmed by Minor Planet Center, confirmed by ALMA observations showing 4 arcsecond deviation in right ascension. Published October 29th, updated November 5th. Statistically significant at 3.7 standard deviations. Real. The stereo, SOHO, GOES 19 observations of extreme brightening in blue color. Published October 30th in ARC preprint number 2510.25035 by Chicheng Zhang of Lowell Observatory and Carl Badams of the U.S. Naval Research Laboratory. Brightness scaling with inverse distance to the negative 7.5 power, blue spectrum. Both confirmed. Davide Farnochia's orbit determination at JPL, 135 kilometers per day, squared radial, 60 transverse. Published in the Small Body Database, updated November 5th, measured at perihelion distance 1.36 to 1.38 astronomical units. Confirmed. The data is on record. The debate is interpretation. December 19th, Earth closest approach, 269 million kilometers, Hubble ultraviolet spectroscopy, Webb infrared spectroscopy, ground-based optical and radio observations. JUICE, potentially releasing data from November 2nd and November 25th observations. The International Asteroid Warning Network campaign running through January 27th. Measurements will accumulate. Gas cloud detected or not. Emission lines present or absent. Brightness evolution measured. Color evolution tracked. Buried in the data will be the answer. Not speculation, not authority, not popularity. Data. On a desolate stretch of desert in Chile, ALMA radio dishes track faint microwave signals from a receding point of light. In Maryland, engineers at Goddard Space Flight Center schedule Hubble's ultraviolet spectrograph for December observations. In California, JPL navigators update orbit fits as new astrometry streams in from amateur and professional observatories worldwide. In Massachusetts, a Harvard astrophysicist calculates momentum transfer rates and exhaust velocities. In Cornwall, Taaz and CT Institute scientists analyze spectral slopes and compare to known cometary chemistry. In Belfast, a planetary scientist models sublimation rates and dust production. In Munich, ES emission controllers review JUICE observation schedules. In Tokyo, Hayabusa 2 team members prepare for their 2031 encounter with a dark comet. And 269 million kilometers away, an object the size of Manhattan, or smaller, or larger, estimates vary, continues outbound from the sun at 68 kilometers per second, shrinking in telescopes, fading in brightness, carrying with it the unresolved question, natural comet, undergoing rare but explicable processes, or something else entirely. 3, iAtlas will not answer that question directly. It will provide data. Humans will interpret. But in a storage vault beneath the McDonald Observatory in Texas, a cylindrical canister holds a single grain of interstellar dust captured by NASA's Stardust mission in 2004. Analyzed, confirmed, older than the solar system, pre-solar grain from another star, proof that we can touch material from beyond. 3, iAtlas is a pre-solar comet, a visitor from another system. Whether it's natural or not, it brings information, chemistry, structure, dynamics, clues to conditions in other planetary systems, windows into exoplanetary formation. One more data point arrives. November 5th, 2025, late evening Eastern Time, updated orbit, fit posted to JPL horizons. Non-gravitational acceleration reduced by 1/3 compared to October 29th value. Still 3.7 sigma above zero. Brightness increased by factor of 5 in green band compared to early October. The comet continues to evolve, continues to surprise. And behind the sun, hidden from our view, 3 iAtlas crosses the frost line, moving outbound, leaving behind the region where water ice sublimates, where carbon dioxide vents into space, where solar wind strips ions from the coma and sweeps them into a tail millions of kilometers long. If it's a comet, the activity should peak near perihelion and then decline as distance increases. If it's something else, the behavior might differ. December will tell us. Spectroscopy does not lie. Atoms emit photons at specific wavelengths dictated by quantum mechanics. Water produces hydroxyl lines at 3085 micrometers. 1.6 micrometers, 2.7 micrometers. Carbon dioxide emits at 4.3 micrometers, 15 micrometers. Carbon monoxide at 4.7 micrometers, 2.3 micrometers. Cyanide at 300 nanometers. Ultraviolet. Dust scatters continuum across all wavelengths with characteristic spectral slope. An emission spectrum tells you what's there and how much. If 3i Atlas lost hundreds of millions of tons of gas near perihelion, the spectral signatures will be unmistakable. If the spectrum shows weak lines, minimal gas, no massive cloud, then the momentum calculation fails. The acceleration cannot come from thermal sublimation. The blue color cannot come from ionized CO+ alone. The extreme brightening cannot come from dust alone. Something else is required. What that something else might be is where science meets uncertainty. Hypotheses multiply, some natural, some not. A solid iron-nickel object heated to thousands of Kelvin by an internal power source would glow blue. Thermal radiation from hot metal peaks in the blue and ultraviolet. Industrial alloys with high nickel content match the observed nickel to cyanide ratio. But what power source? Radioactive decay of short-lived isotopes could generate heat, but requires fresh synthesis within the past few million years. Unlikely for a 7-billion-year-old object. Tidal heating from passing close to stars. 3I Atlas shows no sign of recent stellar encounter. Impact heating from collision with another interstellar object. No fragments observed, no debris cloud, no secondary objects. Chemical reactions releasing stored energy. Possible, but speculative. What chemistry stores enough energy to heat a 2-kilometer object to thousands of degrees? Or an engine, chemical, nuclear, exotic, propulsion system firing to adjust trajectory. The thrust vector has radial and transverse components. Radial, 135 kilometers per day, squared away from the sun. Transverse, 60. Vector sum points outward in prograde, slightly ahead of the radial direction. Consistent with a braking maneuver to reduce orbital energy and adjust perihelion distance or timing. An intelligent system optimizing trajectory for some purpose. But purpose implies intent. Intent implies intelligence. Intelligence implies origin. Where? From what star? Built by whom? For what reason? Sent on what mission? A probe studying solar systems? A derelict drifting for billions of years? An active ship navigating the galaxy? Each possibility raises more questions than it answers. Occam's razor favors simpler explanations. Natural comet with unusual but not impossible properties. Statistical outlier. Rare event in a vast galaxy. We've observed 3 interstellar objects in 8 years. The sample size is small. The distribution of properties is unknown. Maybe 1 in 3 interstellar comets shows extreme characteristics. Maybe the first 3 we detect are biased toward larger, brighter, more unusual objects because those are easier to discover. Maybe 100 fainter. More typical interstellar comets have passed through the inner solar system in the past century, and we missed them because our surveys lacked sensitivity. Or maybe not. Maybe the anomalies mean something. Maybe the data is telling us to look closer. Maybe the technological hypothesis, however unlikely, deserves rigorous testing rather than dismissal. That's what December observations provide. A test, clear predictions. If natural comet, massive gas cloud, strong spectral emission lines, brightness decline, color returning to red or neutral, no further anomalous acceleration. If technological, no massive cloud, weak emissions, sustained blue color, continued anomalies, possible further acceleration events. The measurements are coming. Webb, Hubble, ALMA, ground telescopes, JUICE, Air1 campaign. Data will flood in. Spectra, photometry, astrometry, imaging. Terabytes of observations. Analysis will follow. Papers will publish. Debates will intensify. But one fact remains certain. On October 29th, 2025, at perihelion distance 203 million kilometers from the Sun, the interstellar object 3I Atlas exhibited non-gravitational acceleration measured by NASA's Jet Propulsion Laboratory navigation engineer Davide Farnocchia, 135 kilometers per day squared radial, 60 transverse. Confirmed by ALMA observations showing 4 arcsecond deviation from gravitational trajectory. Published in Orbit, fits updated through November 5th, statistically significant, real, undeniable. What caused that acceleration, whether sublimating ice, hot engine, or something else entirely, remains an open question. The answer lies hidden in spectral lines, brightness curves, momentum calculations, and careful measurement. December brings the data, January brings more. Science proceeds by accumulation of evidence, not by assumption. 3. I-Atlas continues outbound. Silent, distant, carrying its secrets with it toward the interstellar dark. And, in observatories across 7 continents, telescopes turn, detectors cool, spectrographs calibrate, waiting for the moment when the comet emerges from behind the sun into observable sky, waiting to see what the light reveals. Waiting to learn whether the Manhattan-sized visitor is a frozen relic of another planetary system's formation, or something we have not yet imagined. The data will decide. Not speculation, not authority. Data, numbers, wavelengths, measurements. December 19th. Webb Space Telescope, Hubble Ultraviolet Spectroscopy, Ground-Based Photometry, IAW Outer Owen Observations. The instruments are ready, the schedules are set, the coordinates are known. All that remains is to look. Measure, record, and let the evidence speak for itself.